I want you to imagine. A particle appears in a detector, one nobody ever predicted. A ghost in the data. At first, it's dismissed as noise, a fluke, a glitch. But the signal persists over months, years. It passes check after check, calibration after calibration. Soon the whispers begin, this shouldn't exist. The theory forbids it. Yet there it is. That moment, when the laws you believed in start to tremble, that is the point we live for as scientists and storytellers. It's the hinge between known and unknown, between safe maps and the wild frontier. And today, something like that may have happened. In high-energy physics, in massive accelerators smashing protons, ions, or muons, we constantly search for new physics, particles or forces beyond the standard model. Usually, what we find fits into our expectations or vanishes under more scrutiny. But occasionally, a stubborn anomaly defies erasure, a deviation in a decay pattern, an excess of events in an energy window, something that doesn't make sense unless you admit that your theory is incomplete. This script is about that brittle edge. I'll take you into the hidden corners of accelerators, into real experiments where strange signals flickered in the shadows. We'll examine why these anomalies matter, not just as curiosities, but as potential doorways into deeper realms. New forces, undiscovered particles, even a revision of what matter means. You'll meet the key players, the muon magnetic anomaly, the so-called G2 experiments, potential new light bosons like the elusive X17, and modern methods physicists use to separate ghost signals from warm background. You'll see how one impossible hint can remap what we thought we knew, and you'll feel the tension. Is this a miscalculation, a statistical fluke, or the first glimpse of a new layer of reality? I'll also weave in the human drama, the skepticism, the competition, the months of sleepless nights when a team debates whether to publish. Because in physics, revolutionary ideas are born not just in equations, but in doubt, courage, and the willingness to say, maybe we were wrong. By the end of this video, I want you not only to understand how accelerators find anomalies, but to feel the weight of a universe that might still hide surprises. And when I finish, you'll have a question burning in your mind. If a particle that shouldn't exist really does exist, what other impossible things are lurking just beyond our detectors? If you're ready, let's jump. Inside a particle accelerator, what we're really doing is recreating the violence of the early universe, but under our control. Protons are hurled close to the speed of light and smashed together, and for a brief instant, the energy density is so high that matter itself becomes fluid. Out of that storm, new particles are born. Most blink out in trillionths of a second, but the traces they leave in detectors tell their story. Detectors don't see particles directly. Instead, they capture signatures. A faint curl in a magnetic field, a flash of light in a scintillator, a streak of ionized gas. From these scars, physicists reconstruct identities, lifetimes, and decay modes. And here's where the magic lies. If the tracks match what theory predicts, the standard model breathes another sigh of relief. But if the data show excess events or a decay route that shouldn't happen, the ground beneath us shifts. We call these mismatches anomalies. Sometimes they're trivial, a calibration error, a misaligned sensor, bad statistics. But other times they persist through upgrades, through different machines, through rival labs repeating the test. That persistence is when curiosity turns into alarm. Have we found a particle that shouldn't exist? The standard model is breathtakingly successful, yet also suspiciously fragile. It explains quarks, leptons, bosons, but not dark matter, not gravity, not why matter outweighs antimatter. That's why anomalies matter so much. They're cracks in the facade. A single confirmed deviation could point to entirely new sectors of physics, hidden forces, sterile neutrinos, exotic bosons. One famous anomaly comes from studying muons, heavier cousins of the electron. According to the standard model, their magnetic moment, essentially how they wobble in a magnetic field, should have a precise value. But in Fermilab's muon G2 experiment, the wobble was off. Not by much, but enough to raise eyebrows. Billions of collisions confirmed it. And suddenly the question loomed, is this the shadow of a particle we can't see, tugging at muons from the quantum vacuum? Think about what that means. If the anomaly is real, it implies something is hidden in the void, a new mediator particle, or even an undiscovered force. If it's not real, it means we've misunderstood the math, or the data, or the noise itself. Either outcome is explosive, Because if the foundations of your theory need rewriting, everything else shifts too. And here's the cliffhanger. Among these anomalies, one in particular, the rumored X17 particle, refuses to die. If it exists, it might reveal a whole new force of nature. But the experiments claiming it are controversial, even called too good to be true. So is X17 the key to a fifth force, or just a mirage? Every anomaly feels like a door cracked open. But here's the uncomfortable truth. Most of those doors slam shut. The history of physics is littered with ghosts that turned out to be illusions. A bump in the data that faded with more runs, a subtle error in calibration, a background effect masquerading as something new. That's why physicists are skeptical by nature. An anomaly is exciting, yes, but until it survives every attempt to kill it, it's just a rumor. And yet, some rumors refuse to die. Enter the X17 particle. Around 2016, a Hungarian team led by Attila Krasznahorkai reported something strange. They were studying nuclear transitions in beryllium-8, watching how particles spray out during decay. But instead of the expected smooth distribution, they saw an excess, a suspicious bump at about 17 mega-electron volts. The data hinted at a new boson, a mediator of force, weighing in at 17 MeV. They called it, cautiously, X17. Here's why it shouldn't exist. The standard model has no slot for such a particle. We already know the messengers of the known forces, photon, W and Z bosons, gluons, the Higgs. A new boson would mean a fifth force, something no textbook has prepared us for. Critics pounced. Maybe the detector was misaligned, maybe nuclear theory was misapplied, maybe it was simply noise. But the Hungarian group didn't back down. They repeated the experiment with different isotopes, beryllium, then helium. Again, the same anomaly emerged. Same angle distribution, same energy, same impossible bump. And that's when the scientific community split. Some said, extraordinary claims require extraordinary evidence, and this isn't it. Others said, if even a fraction of this holds up, it could be the biggest discovery since the Higgs. But the real tension is this. The anomaly has survived long enough to keep us guessing. Other labs are now racing to confirm or refute it. Some theoretical physicists are even sketching models that could make room for X17, dark photons, hidden sectors, portals to dark matter. Imagine that. A particle that started as a glitch in Hungarian data could turn out to be a bridge to the invisible universe. And yet, what if this is just another mirage? A pattern our minds impose on randomness, the cosmos playing dice and laughing at us. The deeper question is not just does X17 exist, but how do we tell reality apart from illusion when the evidence dances right on the edge of noise? Because soon I'll show you an evidence ladder, step by step, how anomalies graduate from whispers to headlines. And on that ladder, X17 stands precariously, too heavy to ignore, too fragile to trust. When a particle appears in the data, it doesn't instantly become real. It has to climb a brutal ladder of evidence, and most candidates fall off before the top. Think of it like survival of the fittest, but for ideas. Step 1 is statistical significance. Physics is ruled by probabilities, so you need a clear excess of events above background noise. We measure this in sigma, a kind of confidence level. 3 sigma? Interesting, but still possibly a fluke. 5 sigma? That's the gold standard for discovery. The Higgs boson only made headlines after crossing that sacred threshold. X17? It has flirted with high sigma levels, but critics argue the way the data were processed could inflate the numbers. Step 2 is reproducibility. One lab's claim means little unless another team, with different equipment and different methods, sees the same signal. That's why Fermilab's Muon G2 result hit so hard. It confirmed earlier hints from Brookhaven. X17, on the other hand, remains mostly in the Hungarian group's hands. Until independent experiments replicate it, suspicion lingers. Step 3 is theoretical integration. A particle isn't just a bump in data, it needs a place in the grand structure of physics. The Higgs was long predicted before it was seen. Dark matter candidates are framed in dozens of models, but X17? It's a wild card. Some theorists suggest it could be a protophobic boson, a mediator that barely interacts with protons. Others think it might connect ordinary matter to dark matter. But these are patchwork solutions, built after the fact, which makes skeptics uneasy. Step 4 is technological confirmation. The most decisive tests come when new machines, with better resolution and higher sensitivity, go hunting. The LHC, for example, crushed early rumors of extra Higgs-like bumps when no trace appeared at higher precision. The future of X-17 lies here. New accelerators and nuclear experiments are being designed to settle the debate once and for all. Now here's the tension. Right now, X-17 sits awkwardly on the ladder. It's statistically intriguing but unreplicated. It has sketchy theoretical scaffolding, but nothing solid. And the experimental future? It's being built as we speak. Several groups in Europe, the US, and China are gearing up to hunt for it directly. So we are left in suspense. Is X-17 about to climb into the light of confirmation, rewriting the textbooks with a fifth force of nature? Or is it about to vanish under the weight of better data, just another ghost dissolved in precision? Because if it survives the latter, the shockwave won't be limited to physics. It will reshape how we see forces, matter, even the invisible architecture of the universe. If a particle exists that theory says cannot exist, what does that really mean? It's more than a crack in physics. It's a crack in our assumption that reality is knowable, calculable, predictable. Science is supposed to be a map, a set of rules that compress the chaos of nature into elegant equations, but every anomaly whispers something dangerous. Your map is wrong. That's why anomalies unsettle us. They don't just threaten equations, they threaten confidence. The Standard Model, for all its beauty, has become a kind of cage, safe, precise, but incomplete. It ignores gravity. It fails to explain dark matter. It shrugs at the matter-antimatter imbalance. And still, it has worked flawlessly for decades. To admit X-17 might be real is to admit we've been walking with blinders on, mistaking the cage for the cosmos. Critics remind us of history. In the 1960s, claims of new particles flooded conferences, only to be erased with better statistics. In the 1980s, an experiment in Chicago announced evidence of a fifth force affecting gravity. It vanished under stricter tests. The lesson: extraordinary claims fade fast. Why should X-17 be different? But here's the counterpoint. Sometimes the impossible survives. The neutrino was once considered absurd, an invisible, nearly massless ghost particle invented to fix an energy accounting problem. For years, many dismissed it as mathematical fiction. Today, we know neutrinos not only exist but flood through your body by the trillions every second. Yesterday's absurdity is today's certainty, and that is the philosophical shockwave. Every time physics admits a new particle, the universe grows stranger. If X-17 is real, then we're forced to expand our idea of force itself. Imagine, alongside electromagnetism, the weak and strong nuclear forces, and gravity, there might be a hidden fifth interaction shaping reality, invisible until now. A subtle hand guiding particles, influencing matter in ways we've yet to comprehend. For humanity, the idea is both thrilling and humbling. It means our proudest theories are provisional, our certainty temporary. It means we are still children peeking through keyholes, mistaking fragments of reality for the whole. And it means the very concept of impossible may be nothing more than an artifact of our limited imagination. But here lies the tension: belief versus skepticism. To some, X-17 is hope, a path beyond the cage of the Standard Model. To others, it's a mirage, an echo of wishful thinking amplified by human bias. Both sides can't be right. And while they argue, experiments tick onward, preparing to deliver a verdict. And when that verdict arrives, it won't just rewrite textbooks. It will reshape our relationship with knowledge itself. If X-17 stands, we will have proof that the universe still hides fundamental truths in plain sight. If it falls, we are reminded of how easily we are fooled by shadows. Either way, the lesson is the same. The universe is not ours to tame with equations alone. It is wilder, deeper, more defiant than we dare admit. The hunt for X-17 isn't just about checking boxes in a theory, it's about the future of physics itself. Because if this particle, or anything like it, is confirmed, it would open a new chapter of discovery, one with consequences we can barely sketch today. Start with the basics: a fifth force. Right now, our universe runs on 4. Each force has shaped not just physics, but technology. Electromagnetism gave us electricity, radio, the internet. The weak force unlocked nuclear medicine. The strong force underlies nuclear energy. Gravity governs space travel and satellites. Now imagine an entirely new interaction, one we've never harnessed. The applications could be as unpredictable and transformative as trying to explain Wi-Fi to someone in the Middle Ages. Next, dark matter. For decades, we've been chasing this invisible substance that outweighs visible matter 5-1. What if X17 isn't just a stray particle, but a portal, a mediator between ordinary matter and the dark sector? That would give us our first tangible handle on the invisible architecture of the cosmos. Entire industries, entire sciences could be built around interacting with what was once untouchable. Then there's technology. New particles often mean new tools. Lasers were born from quantum insights once dismissed as toys. Semiconductors and the entire digital revolution emerged from quantum oddities in materials. If X17 or its kin reveal a new kind of interaction, we might one day engineer devices that manipulate this hidden force. Communication? Propulsion? Energy? Right now, it's pure speculation. But so was nuclear power in 1910. And don't overlook the cultural impact. Discoveries like this shift not only science, but our story of ourselves. The Higgs boson gave us the missing piece of the Standard Model, a triumphant closure. But X17 wouldn't close a chapter. It would rip the book open. It would remind us that the map is not the territory, that reality still contains undiscovered continents. Here's the irony. The very pursuit of these impossible particles is reshaping the field, even before confirmation. New detectors are being designed. International collaborations are forming. The mere possibility of a fifth force has accelerated innovation. In that sense, X17 already exists, not as a proven boson, but as a catalyst. But the future horizon carries risk too. What if we chase ghosts forever? What if resources are poured into mirages, pulling us away from other urgent mysteries? There's a thin line between visionary exploration and chasing shadows, and history has shown us both outcomes. So we stand at a fork in the road. If the next generation of experiments confirms X17, humanity will step into a physics revolution not seen since quantum mechanics. If the signal vanishes, it will be another humbling reminder of our fallibility. But either way, the hunt itself reshapes science, pushing detectors, theories, and imaginations into places they wouldn't go otherwise. And here's the cliffhanger. What does all this mean for you? Not for labs, not for textbooks, but for the individual human being listening right now. Because if reality can suddenly produce a particle that shouldn't exist, what does that say about the limits you assume in your own life? Think about your life for a moment. Every day you move through the world assuming it runs on rules. Gravity keeps you grounded. Time flows forward. Choices lead to consequences. It feels solid, predictable, safe. But physics has just shown us that even the most trusted rules can be overturned by a tiny flicker in a detector. If the universe itself can surprise us like that, what does it mean for how we live? The search for impossible particles isn't just about physics. It's a mirror for the human experience. We all build models of reality, habits, beliefs, assumptions about what can and cannot happen. And just like the Standard Model, those personal maps work until they don't. Anomalies appear. Life throws something at you that shouldn't exist. A chance encounter that changes your path, a breakthrough you never saw coming, an event that defies the story you told yourself. The question is the same one physicists face. Do you dismiss it as noise, or do you follow it deeper? That's why X17 resonates beyond science. It's not just a candidate particle, it's a symbol. A reminder that certainty is provisional, that possibility is wider than we admit. If nature can conjure a force we didn't predict, maybe the limits you've drawn around yourself aren't as final as you think. Maybe impossible is just another word for not yet discovered. Of course, the human thread also includes doubt. Physicists agonize over anomalies, asking, are we being fooled? Are we projecting patterns where none exist? You and I face the same trap in life, mistaking coincidence for meaning or clinging to illusions. The discipline of science reminds us not every anomaly is real, but some are. And the trick is knowing which ones to chase. If you take this seriously, it changes how you see uncertainty. Instead of fearing the unknown, you begin to treat it as a frontier. Instead of dismissing surprises, you start asking what they might reveal. The discovery of a particle that shouldn't exist isn't just about physics. It's about learning to welcome the impossible in your own life. Because if reality itself is stranger than our equations, then maybe your future is stranger than your plans. Maybe the next version of you lies on the other side of an anomaly you haven't noticed yet. And that brings us full circle. The search for new particles isn't confined to labs or accelerators. It's also a metaphor for living, being willing to spot the impossible, take it seriously, and let it transform your understanding of what's possible. Picture this. A team of exhausted physicists huddled around glowing monitors at 3 a.m. The air hums with tension. They've run the data 100 times, looking for errors, excuses, reasons to dismiss what they see. But the signal remains. A bump where no bump should be. A whisper of a particle that theory says is impossible. In that silence, one truth lands heavy. Either the universe is lying to us, or we've misunderstood it all along. That's the heart of this story. The hunt for X17, or any impossible particle, is not just a search for numbers on a graph. It's a confrontation with reality itself. Physics, at its core, is a promise that the world can be described, predicted, mapped. But when a particle that shouldn't exist appears, that promise fractures. And instead of collapse, we get something better. Expansion. The map grows. The mystery deepens. The universe proves itself stranger than we dared imagine. For you and me, the lesson runs deeper than accelerators or detectors. It's about humility and courage. Humility to admit we don't know as much as we think. Courage to follow anomalies, to risk being wrong, because that's how discovery is born. Science advances not by clinging to certainty, but by dancing with the unknown. So next time you hear about a particle that shouldn't exist, don't roll your eyes. Remember, the neutrino was once impossible. The Higgs was once a rumor. The anomalies of today could be the revolutions of tomorrow. And whether X17 turns out to be real or illusion, it has already done its job, reminding us that the universe is not finished revealing itself. And now I'll leave you with the question. If reality can conjure a force or particle we never predicted, what other impossible truths might be waiting in the shadows? Do you believe this discovery changes everything? Or is it just science fiction dressed in numbers? Tell me below. Your view might change someone's mind.